At 5:30 a.m., July 16, 1945, scientists and dignitaries awaited the detonation of the first atomic bomb in a desolate area of the New Mexico desert, known aptly as Jornada del Muerto, or Journey of Death. They had taken bets on how much power their creation might unleash, but many wondered whether the weapon would work at all. There was, however, one certainty. If the atomic bomb detonated, the world would never be the same.
This story is the great tragic epic of the 20th century. If I were going to give it a theme, the theme would be humankind invents the means of its own destruction.
And in order to do so, scientists, engineers, and the Army teamed up in an effort dubbed the Manhattan Project. In the short span of 2 years, they built an industrial complex with sites across the country that would rival the size of the automotive industry. To manufacture fuel for the bomb, they built the 5th largest town in the state of Tennessee that consumed 1/10 of the electrical power generated in the United States. The bomb builders spent well over $2 billion, almost $30 billion in today's market, to detonate the first man-made atomic explosion just 28 months after scientists set foot in a lab at the Manhattan Project's Los Alamos, New Mexico facility. Nonetheless, that July morning in 1945, many of the world's top physicists watched anxiously at the test site 200 miles south of Los Alamos, awaiting the results of their labors.
5, 4, 3, 2.
But this countdown had really begun 12 years before, when many of these scientists escaped the coming of fascism to Europe.
Once Hitler took power in 1933, the Jews of Europe, especially the Jews of Germany, were under a direct threat. And some of the best scientists in the country happened to be Jewish. Hans Bethe was one, Edward Teller was one, Leo Szilard was one, Einstein was one.
And one by one, they fled Europe to the United States. Scientists found refuge at American universities. In 1938, dramatic news arrived from Germany. German scientists had split the atom by bombarding uranium with neutrons, which caused instability in the uranium nucleus. During this split, mass was lost and was converted into kinetic energy. They had discovered fission, and with it, opened a Pandora's box.
If each of those neutrons goes into another uranium nucleus and causes fission, then the first fission has led to more than 2 fissions in the next generation, and you can see that each successive generation has many more neutrons, and this causes an explosive chain reaction.
If 2 masses of highly fissionable uranium in the form of a sphere and a plug could be brought together with sufficient speed inside a bomb, an exponentially increasing chain reaction with explosive force would result. The implications of the discovery of the fission of uranium would be obvious to scientists in Nazi Germany, and this frightened Leo Szilard, a 40-year-old émigré physicist from Hungary. Politically astute, Szilard wanted to warn President Roosevelt, but knew that he lacked the stature to do so.
Imagine men with heavy foreign accents say they have figured out a way to make a bomb no bigger than an ordinary bomb that could blow up a city. You might well think they were crackpots and throw them out of your office.
Szilard wrote a letter to the president and sought a prominent ally to sign it, Albert Einstein. Szilard, who didn't drive a car, enlisted the help of his friend Edward Teller, an eminent theoretical physicist, to drive him to Einstein's summer house on Long Island.
Einstein read wat dat hier wat Szilard has written, asked a few questions about it, and then said yes, yes, and signed it.
On October 11, 1939, in response to Einstein and Szilard's letter of warning, President Roosevelt formed the Advisory Committee on Uranium. But this abstract new discovery became a low priority for a leadership distracted by a world war that was now 2 months old. A recent refugee of that war, 37-year-old physicist Enrico Fermi narrowly escaped with his Jewish wife, Laura.
They used the opportunity of going to Sweden to collect the Nobel Prize to go from there and then go on to the United States, so that the fascist authorities in Italy at that time didn't know that they were actually not going to be returning to Italy.
Together with Leo Szilard at Columbia, Fermi tackled the first obstacle to the bomb: the question of whether or not a sustained chain reaction could be induced in a uranium reactor. Without the successively doubling power of the chain reaction, a bomb would be an impossibility.
Fermi was one of the few scientists who was talented both in theory and in practice. He loved getting his hands dirty. Leo Szilard was the antithesis of Enrico Fermi. Szilard usually slept late. He soaked in the bathtub to get fresh ideas.
While in the bathtub, Szilard remained focused on the competition, the German bomb effort. He convinced scientists in the US, whose community thrived on openness, to censor their own papers so that they would not inadvertently help the Germans. As the US bomb effort was taking its first tentative steps, news that the Kaiser Wilhelm Institute in Berlin had begun actively pursuing uranium research rippled through the American scientific community. It would take nothing short of a disaster to move the president to take decisive action, and a disaster was not far off. On December 7, 1941, the Japanese attacked Pearl Harbor, sinking 19 U.S. naval vessels and killing more than 2,000 soldiers.
No matter how long it may take us.
The next day, the U.S. declared war on Japan. World War II was no longer just Europe's war.
And their righteous might will win through to absolute victory.
America's entry into the war had a galvanizing effect on its moribund atomic bomb effort. President Roosevelt approved production of the weapon and turned the nuclear program over to the Army. Brigadier General Leslie R. Groves, an expert engineer and administrator, was placed at the head of the Manhattan Engineer District, named after the project's initial headquarters in New York City.
General Groves, having just finished building the Pentagon, was absolutely disgusted to be assigned the Manhattan Project, as it came to be called. He was sure it was a boondoggle. He was sure you could never do such a thing.
But at the University of Chicago, Szilard and Fermi were taking the first steps in proving Groves wrong. They were trying to demonstrate that the fission process could be harnessed by launching a sustained chain reaction in uranium. They built the first primitive reactor in a squash court beneath the stands of the university's football stadium. The reactor consisted of a pile in which a fission reaction could be initiated and controlled.
They did it by piling layers of graphite and then embedding balls of uranium, so that when the neutrons started flying through, they would be slowed by the graphite, collide with the uranium, release more neutrons, and those neutrons would continue in the chain reaction pattern.
This momentous achievement, only detectable by a Geiger counter, meant that the fission process could be sustained. Nuclear energy could be released in a controlled way, as in a reactor, or perhaps cataclysmically, as in a bomb.
It was so crazy that you could put a bunch of uranium together with graphite and the thing would spring to life.
The bomb effort went into high gear. Its first priority was the lack of weapons-grade fuel. Fission is more readily produced in a rare uranium isotope, uranium-235, that occurs naturally at a ratio of 1 to 139 to its less useful twin, uranium-238. Chemically identical, the isotopes were almost impossible to separate. The only workable method in 1942 was electromagnetic separation. In this process, a mass spectrometer used for separating electrically charged particles according to their mass sent a stream of uranium atoms past a magnet. Atoms of the lighter isotope U-235 would be deflected more than those of the heavier U-238 and would be captured one atom at a time. Scientists at Columbia University championed a competing mode of separation, gaseous diffusion. This method passed the isotope through a porous barrier that separated the lighter isotope from its heavier counterpart, but it proved to be technically challenging.
In a square centimeter, about the size of my thumbnail, you've got to have hundreds of millions of pores, and they have to all be the same size. If they're too big, the gas flows through without any separation. If they're too small, the gas gets in there and condenses on the surface, won't go through. So you talk about obstacles.
But if a suitable barrier could be manufactured, it promised a greater yield than the electromagnetic process. Both techniques would have to be done on a massive scale and would prove extremely costly. And if they